Do you know concrete is weak in tension and strong in compression? When a beam bends, top portion of the beam is in compression and bottom portion is in tension. Certainly, we need steel bars on tension side of the beam as concrete is very weak in tension. But sometimes we need bars on compression side of the beam as well. This is due to heavy loads and bending moments. We call this beam as doubly reinforced concrete beam. In this tutorial, I will cover a worked example on doubly reinforced concrete beams as per Eurocode 2. If you have missed theoretical part of doubly reinforced concrete beams, click on this side of the screen to come on over. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London. On this channel, we explore civil engineering and human skills to help us lead more productive, happy, and examined life. In this example, we have to determine the bending reinforcement for the beam, and the cover to reinforcement is 40 millimeter. This is concrete cover. FCK is the compressive strength of concrete, 25 Newton per millimeter square. FYK is the tensile strength of steel reinforcement, be it compression or be it tension reinforcement. So cover is given to us. If it is not given to us, assume 25-30 millimeter, but here it's a little bit higher, 40 millimeter. The span of the beam is 9 and GK is the dead load, 5 kilonewton per meter. QK is live load, 4 kilonewton per meter. And the width of the section is given 230 and height of the section is given 370. Remember that D is not given here, so you have to work out D yourself. Now here we have to assume something. For main bars, means the tension bars, we are assuming that their diameter is 25. Now why we are assuming it? The reason is that we want to work out this D, because D is not given here. D is the distance from center of tension reinforcement to the top fiber. And diameter of compression bar is again phi dash is assumed to be 16 millimeter.
But
Now, yes.
You're saying that we are working out the D, the distance between the center of the reinforcement.
Yes, to work out the
You mean the depth of the beam?
depth of the beam. Yes.
Isn't it given 370 mm?
370 is the height of the beam.
Oh, the total height. Okay.
This is the total height, or you could say it's a total depth.
Yeah, I understand now.
T is the distance from center of tension reinforcement to the top fiber. You can have any sensible assumption. Your answer is not going to be huge.
Can we assume like 20 mm as well for main?
So for main, you can assume 25 or 20. Yeah, for compression, I think assume probably 16. For compression, we normally don't have 20. But for compression, obviously, don't assume it to be 8. 8 is going to be too small. For stirrup, yes, assume it to be 8, but not for compression reinforcement. These are our assumptions. These are not given. If you like, you can use the same assumptions, or you can assume main diameter as 25 or 20, or compression, you can have 16. So ultimate load is found out by 1.5 GK plus 1.5 QK. And GK and QK, these are given to us, 5 and 4. So put these values 5 and 4, you get your design load or ultimate load, which is 12.75 kilonewton per meter. And then in next step,
is the you know, when you said assume the diameter of the bars, is that like a general thing, or is this just for this example? Will it always be assumed 25 for the main bar?
When you are working in actual design office, normally you would assume it because you will not be given D. So you decide about this H and B yourself, and then you assume these bars. Yes. This is just to work out D and D2. And this is the sensible assumption. 25 or 20, diameter of compression bar 16. Then we work out design moment or MED or applied moment. Applied moment is equal to WL square over 8, and we put this W over here from the one that we have worked out. Span is 9, which is given here, and then it's giving us applied moment of 129.1 kilonewton meter. Assume the bar diameter is 25, which I said earlier. A h is given to us, which is 370. H is overall depth of the section. In my last lecture, I gave this formula: D is equal to overall height and take away cover and take away bar dia half. Overall height, if you subtract the concrete cover and if you subtract this bar dia divided by 2, then you will reach at the top. This is giving me effective depth D as 317 millimeter. Now I have found out D. Now I have to find out D2. I think D2 I will find out little later probably. The next step for me would be to find out MRD, the resistance provided by the concrete portion, and this is moment of resistance, 0.167 FCK B into D. FCK is 25, which is given, plugging in that value. B is given 230 and D is 317 that I worked out little earlier. I am multiplying this entire bit by 10 raised minus 6 to convert it into kilonewton into meter. Otherwise it will give me a really very high value and then I will not be able to compare it properly. So remember that if you're getting really very high value which is not comparable to your MED, means that you have made some mistake. And this is one of the most common mistakes in exams. Now once you have got MRD, which is 96.8, you have to compare it with MED. Our MED was 129. Clearly MED is greater than MRD, or MRD is less than MED. So when MRD, moment of resistance, is less than applied, it means that you have to design it as doubly reinforced beam, which means that the difference of moment is taken care of by compression reinforcement. So whatever difference you will get, compression reinforcement will take care of it. Now assume diameter of compression bars as 16 millimeter. D2 will be equal to cover plus phi dash over 2. Phi dash is diameter of compression bar. So this is giving me 48. Now what is missing over here is that because we are not designing for shear, so that's why we have not used the diameter of shear link. But if you like, you can add up the diameter of shear link as well. So here you can see that in this formula D2 and here D, we have not used the diameter of shear link because the assumption is that we are designing it for bending. Now this will give me D2 as 48 and I have to check D2 over X. So from now on, I will follow this recipe, which is here. Initially, you have to work out design load and then work out MED, applied moment. And then you have to work out MRD, moment of resistance, which is provided by concrete part. And if MRD is less than MED, it means that moment of resistance provided by concrete is not sufficient, then the remaining moment will be taken care of by compression steel, which you can see that MED minus MRD here. And then you will check this D2 over X, then work out AS2, then work out Z, and then work out AS1 in this recipe. In this design recipe, I have worked out this D2. And I have to check D2 over X should be less than 0.338. So D2 is 48 and X is, you know that value of X is 0.45D. From stress diagrams earlier, you can see that value of X is 0.45D. So from here, you put value of 0.45D comes from this formula. So 0.45 times D is 317. Now this is less than 0.336 is less than 0.38, which means that it is fine. If it is not fine, then probably increase the size of D by increasing the overall depth of the section. And then we have to work out AS2. AS2 is the area of compression steel. Area of compression steel is taking care of remainder of the moment which is not resisted by the concrete side. So that's why we have MED minus MRD. So MED we worked out 129 and MRD we worked out 96. Make sure that when you work out MRD, it has to be comparable. It has to have some value which you can compare with MED. If you're getting really very large value, then it's not doing the purpose. Now MED take away MRD and do not forget to convert it back into Newton into millimeter. Currently the units are kilonewton into meter. So if you multiply it with 10 raised 6, it will be converted into Newton into millimeter. The reason is that because denominator is in Newton into millimeter divided by 0.85 FYK. FYK is the yield stress of reinforcing bar, which is 500, and into bracket D minus D2. We determine D minus D2. Our D is the effective depth or depth from the center of tension reinforcement to top fiber, which is 317, which we have written here, and D2 we just determined here, which is 48. Now here we have determined D2 and D without taking into account the stirrup, just to simplify the things. Now when you simplify this, the area is going to be 276. Now our initial assumption was that we're going to use the diameter of diameter of compression reinforcement as 16. So if you go back and have a look at this, our required area AS2 is 276 millimeter square. So if I'm using 2 bars of 16 millimeter dia, this will give me area of 402 millimeter square. So I will say that use 400 millimeter square. Any question?
Yes. Could you use 3 number H12s? Because that gives you 336 millimeters squared.
Where? Sorry?
So, you know, your AS2 is 276 millimeters squared.
It is, yes.
Or why have you specifically chosen 2 H16s? Could you use like 3 H12s?
You can use 3 H12s, yes. You can use 3 H12s. Because I have initially assumed that my bar dia is going to be 16. And just to simplify the things, you can use 312s as well.
So with so when you get to the end of your calculations and you end up choosing the bars to use the diameter bar and number,
Yeah.
does that have to correspond with the assumption you make?
Yes. So when you choose different bar to H16, then always check back this D2. All right.
Okay.
It will affect D2. It will not affect D. So it will affect D2.
Cool. Thank you.
Always check that this is satisfied.
I have a question.
Please.
Why didn't you consider the shear link when calculating D2?
Yes. As I mentioned earlier, that just to simplify the things, just to isolate the things for bending, I did not consider a shear link. But normally you would consider shear link and then assume its dia to be 8 millimeter. Because we are not designing here for shear, so that's why I did not consider it here. You're right, it should be considered. And the next step in the recipe, if you go back, is finding out this Z and then finding out AS1. So finding out Z, this is the formula for Z, and K naught dash is 0.167, and if you put all these values, you get Z as 260. Remember that this should have some kind of sensible value. It should be less than D, and if it is more than D or something, it means you have made some mistake. And then I will use this formula for tension steel AS1, which is MRD over 0.87 FYK into Z plus AS2. Now make sure that AS2 that you're using here is the one which is required. It's not the one which you are providing. You're providing more than 276. But AS2 is the actual area, which is 276, which is what we need to put here. Then put this Fy. K is 500, which is given. Z we just worked out as 260 and simply add this up. Now the bars are coming out to be 1132. Now again use 3 H25 bars. The reason is that because I initially assumed that it is 25. That's why I'm using 25 bars. Some of the times your assumption may be incorrect or something. Then always check your D because it will affect your D. You just have to revise D and check if your calculations are fine. Again, 3H25 will give you, if you go to 25 bars and number is 3, so this is giving you 1470, and our required one is 1132. If you wanted, you can choose other bars actually, 1132. You can choose 4 H20 as well. But again, you have to revise D and see that it has any effect. The chances are that it will have minor effect. It will not have huge impact. So then provide H23, H25 bars. And finally, you will draw this diagram. You will draw this value of D that you found out, and you will draw this value of D2. And again, the bottom bars are 3H25 and the top bars are 2H16. So in that way, you have designed this doubly reinforced beam.
Could you please go back to the previous slide for a second? Thank you.
In your practice, would you say it's worth sort of choosing less diameter steel
Yeah,
bar?
we can. Yeah. So if we choose, so this will affect D. So this will affect D. If we are choosing 20 bars, H20, then D will be equal to 370 minus 40 minus 20 over 2, so 370 minus 50 basically. So this will give you 320. So D is 320 millimeter, and this will not affect much, I believe, the MRD. So if I'm using 320 square into 230 into 25 into 0.167 into 1 exponent minus 6, it's giving me 98.3. So 98.3 means it will slightly affect AS2, but again, it will not be huge impact. So I'm getting MRD by using this D as 320. I'm getting MRD as 98. And then again, this will have a slight impact on this, but it's not going to be huge impact because it's a difference of 1.5 kilonewton meters. So I believe it will not create much influence on AS2, to be honest. So you can work out, if you like, that 98.2 kilonewton meter and D is 320 mm. Let's see if 129.1 minus 98.2 into exponent 6 divided by 0.87 times 500 times into bracket 320 minus 48. So instead of 276, it's giving me 261 millimeter square when I'm changing D and when I'm changing revised MRD. Let's see what is change in Z. So change in Z will be equal to 262.5 for Z by changing this D to 320. And then finally, AS1 will be equal to MRD. MRD was 98.2 times 10 raised 6, 0.87 into 500 into 262.5 plus this AS2, which is 261. Let us see what is the difference by using this revised values. So AS1 is giving me 1121 millimeter square. So the required one is going to be less because you're using less diameter bar. If you were assuming it to be, say, 32 millimeter H32, then certainly it will affect quite a lot. So required is going to be less. Probably you don't need to check it as well, even if you're using 4H20. The 4H20 will be a little bit of economical solution because it will give you 1260 millimeter square. Does it make sense?
Yeah.
Sir, is that X value always, is that a constant 0.45?
X is 0.45 of D. Yes.
Yeah, okay.
It is constant by the design code.
Okay.
And then finally, draw this diagram to show that whatever you're providing, it's there. Any questions?
Can you draw that diagram? I've seen in like one of the tutorial questions, it asks you at the end of working all of that, asks you to draw out.
Yes, I know what you mean. Yeah.
Was it like a force diagram or something?
Yeah. So what you can do, you can work out this FCD, which is 0.85 into FCK25 divided by 1.5. This will give me 14.2 Newton per millimeter square. And FSD will be equal to FYK over 1.15. It will give you 434.78. So I will say 435 FSD. And then you need to work out this FS2 and FC. So force in FC is equal to this times this. All right, this is FCD. So it would be up to this point. All right, so it will be B times S times FCD. Your FC is going to be BS into FCD. Your B is 230. S is equal to 0.8 X 0.8 times 0.45D 0.8 times 0.45 times this is 317. So this will give you value of S. 0.8 times 0.45 times 317, 114. So this is value of S. So 114 times FCD is 14.2 114 times 230 times 14.2, and I will divide it by 1000 to convert it into kilonewtons directly. So this is giving me 372.7 kilonewton FC. Then you will draw this diagram and say that FC is 372.7 kilonewton. And then you will write value of Z as well. And FS2 is compression steel. So it would be FSD times AS2. FSD is the stress in steel, which is 435 times area of steel is 276. AS2 is 276. All right. So 435 into 276, and I will multiply it with 10 raised minus 3 to convert it directly. This will give me 120.06, but I'm writing 120 kilonewton. So here value of FS2 is 120 kilonewton, and then remaining is FS1. FS1 is equal to FSD into AS1. AS1 is this one, 1132. So 435 into 1132. Was it 32? 32, yes. Multiplied with 10 raised minus 3. So this will give you 435 times 1132 times 492.4. This is 492.4. Now 120 points plus 372.7. Now you can see that when you add these two forces up, it should be equal to this one. Because I have rounded it off a couple of times, when you add 120 to 372, it comes out to be 492.7. Here it's 492.4. The reason is that I have rounded it off a couple of times. All right. If the diagram is given to you, then it's just putting it into the values. Would it be difficult?
No, if you have to diagram, well, if you say what we've got to achieve, like SC or FS, then that's fine, and the diagram. But
okay. Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.